Yeah, so this is a joint work with Samira Akhavan and Frederick Chibu. This is on basically learning neural networks for PDEs, especially for interfacial PDEs with interfacial jump conditions. And the purpose is basically accelerating simulations. My application has changed from NVIDIA to Genentech in the meantime, so this is an overview. I want to advertise this as an open source project. The purpose is basically providing a three-dimensional solver that goes from this fully discretized traditional numerical solver state to one that integrates with neural networks all in one framework. And the purpose here is basically to find these hybridification strategies between automatic differentiation and finite discretizations, because in most cases, especially the ones that we are interested in, there are usually very robust numerical discretization methods that actually work, and we want to be able to use them for our industrial applications. So the type of problems that basically motivate this kind of work is essentially this multi-scale problems, where you have this on the smallest scales, like atoms or antibodies or molecules or proteins, and there's always some macroscopic phenomena happening and you're basically interested in predicting these macroscopic behaviors or inferring some parameters. There are many examples of this, like in epitaxial growth design and dynamics model, which uses a hybrid that goes from partial representation to continuous representation with these jump conditions and free boundaries. There's also this case of aggregation and folding of these proteins, the macromolecules, which also is amenable to the same type of modeling and is of interest right now. Generally, these problems are based on calling these interfacial transfer processes, where there's this idealized surface in 3 dimensions. There's a lot going on inside that surface, but a partial representation, but we also usually have these phenomenological models or different type of this, and that gives us these kind of boundary conditions on these interfaces as separate different phases of matter. And there's usually sometimes it's transporting across the medium. And from a mathematical point of view, most of the problems that we're interested in can be represented in this kind of elliptic PDEs, where there's this jump condition. Usually you have like a geometry which is separating omega minus and omega plus, and on the interface you have a jump in the solution and also in the flux, the gradient across the solution. And this would be like the familiar Boltzmann problem, or electrostatics, or many other things. And this is the way to solve these problems is best done with the level set method, Osher and others. Basically, level set is basically an implicit representation of the geometry, and that allows for computing different geometrical information about the object, and also allows you to evolve these interfaces freely. And the coupling happens across with the PDE itself through this velocity field that has to be physically motivated. This is especially useful for problems where there is a topology change, like the one I just shown here, and which is actually a lot happening in, let's say, material sciences and in epitaxial growth, for example. I keep referring to this because this is something that I've been working on, and I know that it's actually works on those problems. But there's a lot of applications, and we're interested in developing this computational framework which is efficient and scalable. It has to address long time scale simulations, and we're interested to scale to large spatial domains. And for example, in the case of antibodies, that's basic concerns. What I'm doing right now, you would like to be able to simulate a lot of these antibodies and for a really long amount of time. And the idea is that there are some developments in machine learning that allow for accelerating simulations. But the problem with those is that this is usually not very accurate enough from numerical accuracy standpoint. But we know how to fix those when we're treating them in a numerical discretization fashion. And the other aspect of this is it has to resolve high frequency features in the solution. And this is basically there are multi-scale patterns that we measure in solution, and we want to be able to represent these things. And it has to have native support for optimization. So it has to be end-to-end differentiable, and because we want to maybe have some macroscopic observation, and we want to train for optimize for some parameters of the model. And it has to also be able to allow us to integrate physical players into this framework. So all of these things are very ambitious, but we tried our best to basically accomplish this with three main components, I would say. The first one is obvious, as we mentioned. They are basically using finite discretizations to train neural networks, but not exactly with all the parameters of the network, but just treating the spatial and temporal gradients, replacing them with finite discretization. I mentioned this. I'll go into details of that later. There's also following developments in compiler-based parallel differential programming. This is mostly developments in, let's say, we basically use JAX, and we follow the trend on that aspect because it allows us to create efficient code and also with support for differentiability. Another aspect is actually using compact neural networks. We are not interested in learning huge neural networks and that present a solution. We want to do it as shallow as possible. So there's very few training parameters in the model. But then we also use a lot of these advances from different areas. There's frequency encoding, so like the multi-resolution hash keys and stuff like that. These are all already available in the online code. The promise is if you could learn these kind of operators, you will accelerate simulations and enable simulating new processes of interest. There are generally, I want to now focus on this presentation specifically is only focused on how do we treat how do we evaluate the residual of the network. Most people just use automatic differentiation with respect to the neural network parameters itself and also with respect to the gradients, the implicits. We just disagree with the second part. We don't want to be actually doing AD on the output space with the input. And in order to motivate that, there are many reasons that this kind of differentiation is not really robust, and it shows itself in the type of results that we can get out of existing frameworks and also softwares. But I would just go with the fact that we already know how to discretize neural networks up to with very good refinement and accuracy, and we just don't want to use these things to train the network. Besides, there is actually some argument that the discretization itself is actually mathematically informing the neural network about some conservation laws for each grid point that you're training over, and also, for example, here, if you just do a simple finite volume discretization, you're actually enforcing fluxes across the little interface. There is a small voxel around the grid point. This kind of, let's say, things that are already considered in maybe centuries of development in numerical analysis, I think is really not good to throw away. And just look at this also shows in our results. Basically, we separate the differentiation into with respect to input, and we do that with finite discretization, and then the automatic differentiation takes care of the rest. And first time we did this, it was in around 2019, 2020, and we just wanted to train some inverse operators mapping solution to some hidden parameters. And this was what we did. It's something called semantic autoencoder has come out, and we just replaced the decoder with a full differentiable solver that was doing a direct solve on a finite discretization method, and also on these multi-quadratic regular basis functions. And we then encoded our hidden parameters in terms of some eigenfunction expansion, and that was how we encoded symmetries of the problem into it. Essentially, we trained this on a static problem and also in some time transient problem, the Berger's equation actually. And it was very clear from the results that the network is now learning the solutions pretty regularly. There is convergence actually with adding extra computation. You actually get better neural networks, which was the thing we needed. And also, the training was much faster. With only 10-20 iterations, we could already converge to really good results. And there are also, there's this claim that around 2020, people used to say these things more often, that quantization cannot handle cases where noise and stuff like that. But then the fact of the matter was that in the 80s and the 70s, there were some numerical methods that were actually designed for this kind of thing. But there were some problems with them. For example, you had to learn some parameters of discretization itself, the shape parameter of the radial basis functions and the placement of the seeds in that method. These were parameters that need to be actually learned. So we actually handled this by the encode of the network itself, which was now also identifying the best discretization. So what you see on the right side is basically the location of the seeds for the shape, for the multi-quadratic basis functions for the RBF, which was actually trained by the network. This increased the accuracy, and again we retained the same kind of nice features. And but then the problem with this approach was this is not really scalable to, if you want to do a direct solve, and this again has a lot of issues for going to 3 dimension, and we're not even interested in higher dimensions, just 3 for our applications sufficient. So this was when we decided to create this numerical method, which essentially is completely, that turns the problem of optimization, of solving the problem into like a simple minimization problem of the residual itself, but also the fact that the neural network could be evaluated during training at every point in the domain separately actually allowed us to get rid of a lot of the communications by just creating these kernels that would implicitly create a computational cell at any random point. And the residual step is now still coming from discretization. In this case, it was this discretization by Bochkov and Jibu in 2020. And although the method itself is a structure, you could in this way just pretend as if this was this is applicable to this case of random structure data points. And yeah, so essentially this has some really good features, because now the problem of training becomes like data parallel training of the network, and you only compute the different batches, the gradients of the network at different batches of the points in the space, and just sync the gradient at the end of each epoch and go to the next one. And in this case, actually, we could have a lot of the same features that that was basically required here. So this is the details of the numerical discretization. I won't go into the details of exactly how that is done, but essentially there is some issue that comes out when going this route, is that you need the problem of this route are really if condition. This plot shows the variation in the solution error, which increases when you go to more and more if condition problems. And in this case, that was by the ratio of the diffusion coefficient from the inside and the outside in the 2 domains. And so what we did here was basically the simplest fix for the Jacobi preconditioner that was just discussed in this symposium. And this could already give us some improvement in the results, but that's an area that we are still trying to advance. And then there's this numerical results that we tried these different places. The simplest one was this sphere, the spherical interface, and with some variable diffusion coefficient and the source term. The good thing about this was that the method still is convergent, in the sense that the network gets better and better as we increase the training points, and then the eligibility norm. And the other aspect is that you also get good gradients out of this method. Then we made the geometry a little bit more complex. Here, this is a standard test, essentially. And in this case, it was a little bit more difficult, because the problem is more preconditioned, but still the convergence property is there. And we also observed that we could actually, the solution, the bounded network would give you better solution for the resolutions first. This is also a common fact. So and this actually hints to using this kind of multi-resolution or multi-grid kind of solver that we are exploring at this point. In terms of the scaling, we basically tested this on one DJX machine with 8 GPUs. This was the first version of the code, and there was an issue with that back then the JAX was not actually the PMAP. You couldn't actually JIT a P-map function, basically in the first version of it, and that actually hindered some optimization that we could do. But still, these are good scaling, I would say, on one machine. And in terms of, you can actually go as high as like 68 billion grid points effectively on one of those machines. There's one thing that I want to point out is that every result I've shown in this presentation, these are all without batching. But with batching, the latest version of the code, you can simulate all the systems with only 2 gigabytes or 1 gigabyte of GPU memory actually. So the current thing that we are actually trying to fix is these preconditioners. These are also we tried these are like benchmark essentially the Boston-Boltzmann equation and the different diffusion coefficients is to jump with a factor of 40 in this case. Still, it gives us very good results. It's comparable to other methods in the field. But we think that this is almost without any preconditioning, just a simple Jacobi preconditioner. And we're hoping to basically explore proper preconditioning methods and implement these things. There are some ongoing work, which I won't get into much details about it at this point. But I just want to finish by earlier, I think, but by advertising again that there is a framework. The goal here is essentially to support all the different types of preconditioners and also allow the researchers in this field to have differentiable properties. Maybe you want to train your preconditioner, maybe you want to integrate differently with complex discretizations, and you want to support the three-dimensional research. These are all the building blocks of all of that is already there. And we also support different types of models, neural network models, and different types of encodings. So essentially, it should be a good starting point for hopefully we can develop it together. Yeah, thank you.
Questions for Gloria? I'll start off with a question. Yes, you talked about sort of scalability analysis. What's sort of the bottleneck to the scalability of the system? Like, what would stop you from taking this to, a trillion grid points, effective grid points, or in the computations? What's sort of the bottleneck step?
Do you think so? Right now, everything is completely local. We basically have one kernel that we can apply it on any point, and there's really no communication during aggregating the residuals from different points as a partial residual. So there's really nothing, I think, in this sense. The network itself is also tiny. All this is also with maybe 100, 200 parameters. There's really not anything from that. But what is really the biggest struggle is basically having these kind of solvers that can take these residuals and train the parameters. There's really, the only thing that stopped us from going further was lack of infrastructure. We can have more machines to scale these things, and also right now I don't have access to these things anymore. But so I don't know. I don't think there's any. And also this code is fully JIT compiled also, and we tried our best to make sure that everything is as efficient as it is, and that took 2-3 years. I don't know, at this point I think that the biggest thing that is on our mind is the preconditioners and improving the solver. But there are also some research from this, I think Raymond Terminalo and others are also trying to develop this preconditioner on a completely patch-based local. We're trying to learn from them and see what we can do.
Great. Any other questions for a speaker? All right, people are excited for the break. We'll go ahead and take a break then. I think we'll reconvene here for the last 2 talks. It's scheduled to happen at 3:30, so I'll meet back here at 3:30, 15:30, and hear our last 2 talks, and see you then.